In the last video, we looked at a fairly simple example of an analysis, a principal components analysis, to reduce the dimensionality of a data set. And we're going to follow that up in this video with a principal components analysis of a slightly more complicated data set. So this data set is data on 33 athletes competing in the decathlon, and we have the 10 disciplines represented here, the M100, M400 and M1500. So these are the times in seconds for the 100 meters, 400 meters and 1500 meters. M110, M110 is the time to finish the 110 meters hurdles. Pole is the pole vault height. High J and long are the results of the high and long jumps. So these are all measured in meters. And then weight, disc and javel are the lengths in meters that athletes were able to throw the shot put, discus and javelin. So let's scale the data first. So let me just see where I do that. So I'll scale the data. So we talked about scaling the data in the last video. It's often the first step for a principal components analysis to scale the data so that all the variables have a mean of 0 and a standard deviation of 1. And then I'm going to skip ahead to doing the principal components analysis. So here we go. So in the last video we used the function called princomp, this one, but as I mentioned there are different functions all designed to do principal components analysis, always slightly different syntax, and they tend to give similar results, but everyone has their own favorite PCA function. So for this video I'm going to use this one here, the doD.pca function. So I'll do that and let's summarize what we get. So we get slightly different output from the princomp function. We can see more details as usual using the help. And so what I want to look at here is what it's calling the cumulative projected inertia. So this is what we described in the last video as the cumulative proportion of variance explained by each component. So the first component explains 34%. The second component explains 26%, and if I add 34 and 26, I get 60. So the first two components are able to explain 60% of the variance in the data. So that's not too shabby. And it's much easier to work with 2 dimensions than a higher number of dimensions. If we did go to the third dimension explains another 9.4% of the variance, so we'd be up to 69.68, but it's a lot more challenging to work with 3 dimensions than 2. So in this case we're just going to stick with the first 2 dimensions and see what that will reveal about the structure in the data. Let's take a look at a Scree plot. So this shows graphically the values that we just went through. So the percentage of explained variance is on the vertical axis and the dimensions on the horizontal axis. So the first dimension is explaining 34%, the second dimension is 26%, and then there's a big drop down to the next one, which is only 9.4%. So this again kind of reinforces the notion that we can probably get a good summary of the structure in the data if we just use these first two dimensions, because they're explaining quite a bit together. They're explaining over 60% of the variance in the data, and then there's a big drop for all the other dimensions. So that this kind of plot is useful in that it tells us that a two-dimensional solution is probably going to be quite helpful. We talked about the loadings last time. So if I look at the loadings for the first two principal components, I think I'm actually going to redo that, but round these numbers so that we don't get too distracted with all those decimal places, because it's all a little bit much. Okay, so if we look at the numbers for the first component, in terms of magnitude, they're all kind of roughly in the same ballpark, kind of between 0.17 is the smallest, 0.43 is the biggest, I think. Some of them are positive, some of them are negative. So we could maybe think of this first component as being an overall performance score, maybe. And if we look at the signs as well, the positive signs are for the running events. These are all the positive signs. So the running and the hurdles. And all the negative signs are on the jumps and the throwing. So jumping and throwing seem to get negative scores, negative loadings, sorry, got to use the right word, whereas the running events and the hurdles get positive loadings. Let's think about that a little more. Let's think about how the variables were measured in the first place. So the running events and the hurdles, the measurement was time to finish. So a low number is better, because that means you finished the race quicker. Whereas with the jumping and throwing events, a high number is better, because that means you either jumped higher or further, or you threw the object, the javelin or discus or shot put further. So that kind of suggests that maybe we should reanalyze the data but switch the signs for the running events. So we'll come back to that idea. Let's look at the scores. So we look at the scores using this function here. So these are the scores for the 33 athletes. Okay, I'm not going to dwell too much on that just now. What instead I'm going to do is take a look at a biplot of the results. So this kind of illustrates the point I was making here with the loadings, that we've got all the running and hurdles, so the 100 meters, 400 meters, and 1500 meters, and the 110 meters hurdles. These arrows are all pointing in this direction. So on the first dimension, they're all pointing to the right. And then everything else, the jumping and throwing events, are all pointing to the left. So it makes the interpretation of the two different dimensions a little bit challenging. So, and we get the same kind of picture when we just look at the variables in the circle of correlations. All the running and hurdles are pointing to the right, and all the jumping and throwing are pointing to the left. So I'm going to do what I suggested. I'm going to go back to my data, and I'm going to change the signs on the running performances. And what that will do is it will mean that all the variables now are set up in a way that the higher the number, the greater the number, the better the performance. So I'll do that, and then I'll redo the analysis, and then I'll summarize it, and you'll see that these numbers are exactly the same as they were before. And that's because the principal component analysis, the way it works is it's looking for structure in the data, and changing the sign on a variable doesn't change the structure of the data in the sense that we're looking for here. What it helps, though, by doing this sign change is it's going to help with interpretation. Okay, so let's look at the loadings now. So now you can see all, and let's round them again so we don't get overwhelmed with all those decimal places. There we go. So just focusing on the first component, so this particular function labels it CS1. All these numbers, the magnitudes of all these numbers are the same as they were before, only now all the signs are consistent. Doesn't matter too much that they're all negative. It's just as easy to work with whether they're all negative or whether they're all positive. The idea, though, is that they're all the same sign. So that isn't necessarily what you want to do in any PCA, principal component analysis. It's just it makes sense in this example, because in this example, we thinking about the subject area, if we are looking to describe the first dimension as representing some overall measure of performance, then it makes sense that we need to have the data measurements, the original data measurements, all correspond to larger is better. And when we do that, we get a nice consistent interpretation of the first component. And we'll see that if I draw the graph, the biplot. Actually, this one's the no, let's go back. I'm skipping ahead. If I look at a graph of the variables, okay, because now they're all pointing in the same direction. So we can think of dimension 1 as representing overall performance, because dimension 1 is on the horizontal axis, and all the loadings are pointing in the same direction in terms of dimension 1. Okay, I'm not thinking about dimension 2 yet, we'll come to that, but just thinking about dimension 1, all the arrows are pointing to the left. So that means dimension 1 is an overall measure of how well the athlete is performing, because they're running quicker, they're jumping higher or further, and they're throwing random objects further. Not random objects, they're specific objects, the javelin, the discus, and the shot put. Okay, what about dimension 2? What's dimension 2 doing? So dimension 2, if the way to look at the loadings is to look where the large magnitudes are. So they could be either large positive numbers or large negative numbers. So let's see. So the large positive numbers, we got a 0.48 on the shot put, we got a 0.5 on the discus, and we got a 0.37 on the javelin. Those are the three largest positive numbers. So those are the throwing events. And let's look at the large negative numbers. We've got a minus 0.42 on the 1500 meters and a minus 0.35 on the 400 meters. So it looks like one way to interpret the second dimension is it's explaining variation between athletes in terms of the contrast between, on the one hand, how well they do in the throwing events compared with how well they do in the longer distance runs, the 400 meters and the 1500 meters. So it looks like this dimension is explaining variability in terms of that contrast. So either athletes that do really well in the throwing events but pretty poorly in the longer distance runs, or vice versa. Athletes that do well in the long distance runs but don't do very well in the throwing events. And you could imagine that there's probably some decathlon athletes for which that is the case. They're really strong throwers, so they do really well in the throwing events, but they don't do very well in the long distance running events, or they do really well in the long distance running events, but they don't do well in the throwing events. So that's what the second dimension seems to be picking up. The first dimension is overall performance, so it's explaining variability between athletes that do well overall in all the events and contrasting those with athletes that do really poorly in all the events, well, relatively poorly. If you're a decathlete at a high level, you're doing pretty well at everything, but relatively speaking, it's discriminating, or not discriminating, it's explaining variability between the strong athletes and the less strong athletes. And the second dimension is picking up that difference between the athletes that are doing well in the throwing events relative to the long distance running events, or vice versa. Okay. So that kind of takes us as far as we can go in terms of the principal component analysis. We can push this particular example a little bit further though, because we happen to have another variable, this one here. So this variable is the overall score of these particular athletes in I think it was one of the Olympic Games. I can't remember offhand which one it was, but it does say in the accompanying online notes for this example. But anyway, this is information that has not been used in the principal components analysis, but it is information that's available to us. So it will be interesting to see whether the principal component analysis has any kind of relationship to how well the athletes did in this particular Olympic Games. So let's see. So what we could do is we could pick off the scores. So these are the scores for the athletes, the principal component scores on the first dimension. So remember, the first dimension we said was picking up overall performance. So what we might expect to see here is a linear relationship between the first dimension of the principal component analysis and the final decathlon score for each of these athletes. And if we do get a fairly strong linear correlation between these two variables, that's going to tell us that the principal component analysis has been quite successful in summarizing the structure of the data set, in terms of it's been able to pull out of a very high dimensional data set, like a 10-dimensional data set. It's pretty high dimensional, and it's been able to condense that information down into a single dimension that is explaining the structure or the variability of the entire 10 dimensions. It's able to reduce the dimensions down to 1. Before I actually draw this graph though, one thing to note is that these decathlon scores, the higher the better, whereas these principal component scores, that was reversed because the loadings were all negative. All the arrows are pointing to the left. And so when I draw this graph, I'm probably going to get a line that has a negative slope rather than a positive slope. So they're going to be negatively correlated. But all I'm looking for is the overall magnitude of the correlation. I'm not worried if the sign is backwards, because principal component analysis doesn't worry about signs overall. Okay, enough talk. Let's just draw the graph. So it's pretty good. There's a fairly strong negative correlation between the decathlon scores on the horizontal axis and the principal component scores on the vertical axis. So what this graph tells us is that the principal component analysis is quite successful at summarizing the overall performance of the athletes in that first principal component, in that first dimension. So the best athletes were over here on the right of the graph. So the person marked number 1, they won the gold medal. Number 2 won the silver, and number 3 won the bronze. In terms of the PC1, the first principal component, according to that score, it should have been athlete number 2 that did the best, but it was actually number 1 that got the highest score. And then the second highest principal component 1 score was number 6 on the overall score. So it's not perfect by any means, but you wouldn't expect it to be perfect because we're trying to summarize 10 dimensions in a single dimension, and so it's not going to be perfect, but it's pretty good. Okay, so that's an example, a second example of a principal component analysis.